lecture series on differential equations for undergraduate students. We are doing partial differential equations. Today's topic is Fourier integral and transform method for heat equations. We have learned about the heat equation and its solution using the Fourier series method. Today we will learn the solution of heat equations using Fourier integral and the Fourier transforms. So, let us just try to see what is our practical problem. Find the flow of heat in infinite bar with lateral insulation. That says is that now my bar is infinite one, it is ranging from minus infinity to plus infinity. Again it is laterally insulated, that says is that heat is not moving in the lateral direction, it is flowing only into the x direction. Practically infinite bar, what does we mean is that is a very long bar, a very long wire in which this heat is flowing. We have to now formulate this. So, again the heat equation, that the equation which is governing this flow of heat, that would be same as that heat equation known to you, del u upon del t is equal to c square times del 2 u over del x 2. But now my bar is infinite, that says is that in usual heat equation when we were solving, we used to take the boundary conditions, that is when the bar was of a finite length, we used to take that temperature was the flow is 0 at the end points. Now here because it is infinite one, that is x is ranging from minus infinity to plus infinity, we do not have any boundary conditions, but we do have one initial condition, that is initially the temperature of the bar is say Fx, that is what we are having is we are having Ux at 0 is Fx. So, now what we are interested is, if we see, if you remember, that is we have done this heat equation del u over del t is equal to c square del 2 u over del x 2 for x belonging to one interval. So, 0 to L and then t is 0. There we had the boundary condition at 0 as well as at L, that is u 0 t is 0 and u L t is 0 for all t. That we have solved it using the Fourier series method. So, we have got the solution in the terms of the Fourier series of the function, where we had the function initial condition f x, and that we had is, that is if we say is that it is periodic with period 2L, that is we have taken the odd extension of that function f x which was defined on a finite length. Now, here what we are having is infinite bar. So, there is no use of taking that kind of solution, or it is natural that we think in the terms of Fourier integral, because we are having it infinite bar, that is my function f x now cannot be periodic. So, we do have one initial problem, that del u over del t is equal to c square times del 2 u over del x 2, x is ranging from minus infinity to plus infinity, t is positive, with initial condition u x at 0 is f x. Now, how to solve it? Again we will go with the same method, that is variable separable method. So, separation of variables we will use, let us say the solution u x t is, the function is product of two functions, one of x only, another is of t only, f x into g t. So, if I differentiate partially this function with respect to x and with respect to t, we do get is that the second derivative with respect to x of u x t would govern only, that is the second derivative of f with respect to t with respect to x only, and g t would be the constant, that is we have got it f double dash x g t. Similarly, we require here the first partial derivative with respect to t. So, du over dt would be f x dg by dt, or we can write f x dot into g dot t. Dot means is that derivative with respect to t. Now, substitute this del 2 u over del x 2 and del u over del t in our this given equation, and then divide it by c square f g. What we do get, if I do substitute it here, I would get is f x times g dot t is equal to c square times f double dash x g t. If I divide it by c square f g, so let us write it this first time, that is c square times f double dash into g t divided by c square f x g t, what we would get it f double dash x divided by f x is equal to g dot t divided by c square g of t. Now, this left hand side is having only one variable x, the right hand side is having only one variable t, and we are saying is that these ratios are equal, where c square is certainly a constant. These ratios could be equal only if this ratio does not contain any variable, that is this ratio must be equal to k. So, let us say that it is some constant k. What it says is, now we have got two ordinary differential equation, one from here, that f double dash x is equal to k of f of x or f double dash minus k f, and another is equal to 0, and another g dot t minus c square k times g t. So, we have got the two ordinary differential equation, f double dash minus k f is equal to 0 and g dot minus c square k g is equal to 0. Now, let us take usually we used to take this first equation to solve the first, but now let us just try with this second equation, because the second equation is first order equation, is much easy to solve. So, let us try with this second equation first. If I am taking this second equation, this is first order equation, del g upon del t is equal to c square k g. We do know its solution is nothing but e to the power c square k t. Of course, there must be some constant, that constant let us take it as 1. Now, if this is the solution of second equation, let us say the what kind of the solution of the first equation we do have. First is second order equation. We have already done a lot many times this kind of equation in this partial differential equations itself. It do have, that is depends upon that what is the value of k is. If the value of k is 0, we would get the solution of the form a x plus b. If the value of k is positive, we would get the solution in the form of a times e to the power x root k x and plus b times e to the power minus root k x. And if k is negative, we do get the solution in the form of a cos root k x plus b sine root k x kind of thing. So, finally, what we would get the solution of our partial differential equation, that is we said is f x into g t. So, it would be f x, that is the solution of the first equation, into e to the power c square k t. Now, whatever the form of solution we do have for the different values of k, that simply says is that that function a x plus b or a e to the power root k x plus b e to the power minus root k x and so on. What we do have is that as t is increasing, because that would be a function of x only, and t is involved over here. So, if t is increasing, this function would go on increasing. What it says is, with respect to the time t, it will go on increasing, while we do know that heat flows from the higher temperature to the lower temperature. So, it cannot go on increasing with the time t. So, that is not of any practical importance if I am taking k to be positive or k to be 0, because at k to be 0 it would be only depending on x, and that is not with, it is not depending on t, again that would not be of any physical significance. So, we have to take this k as negative, only then it would have any practical significance, this heat flow of the heat. So, we do take k to be negative. So, let us say k is minus p square. K is minus p square means is my g t would be e to the power minus c square p square t. Now, this equation, first equation now we do come, the first equation will now become f double dash plus p square f is equal to 0. We do know its general solution is a times cos p x plus b times sin p x. Since we are using this p, we are writing it as the constants as a p, that is depending upon p, whatever the p would be. To find out this a p and b p, we have to write the complete solution, and then we have to use the initial condition. So, what we are getting is u x t. Now, I am using this third parameter p, because p we are using here k is equal to minus p square, as a p times cos p x plus b p times sin p x e to the power minus c square p square into t. Now, at t is equal to 0, this initial condition u x comma 0 is equal to f x. If I try to satisfy for every p, I would be getting different a p and b p, and that what we would be having is, that is we are not able to satisfy like that. So, for doing it we require either we use, as usual we used to do, is that is we sum up all these p in the integer values we have taken. The reason for to take it as integer value used to be that we were having the boundary condition that has given me certain h, that is we have got this function was not in the exponential forms or something like that kind of things. Now, here we do know this f x, and there what f x was defined in a finite interval. So, we could take its odd extension or even extension depending upon whether we are left with the cosine series or the sine series, but here this f x is not periodic, rather we cannot make it periodic in any manner, because it is already defined on the whole real line. So, it is better if I use the idea of Fourier integral, that is I should use this p as real number, and we take for all p positive 0 to because p has to be positive. So, p positive 0 to infinity. Let us just see what is the Fourier integral which I am talking about. I am just recalling it because you have done long back. So, we do have that any function f x can be written as integral 0 to infinity a omega cos omega x plus b omega sin omega x d omega, where this a omega is 1 upon pi integral minus infinity to plus infinity f t cos omega t dt, and b omega is 1 upon pi integral minus infinity to plus infinity f t sin omega t. This we had learned in when we are doing is that Fourier the function which are not periodic, we had learned in Fourier integral. So, the same technique, same method we would apply over here. So, what we do get is that if I just write it at what we do get f x as 1 upon 2 pi integral minus infinity to plus infinity of integral of minus infinity to plus infinity f t cos omega x minus omega t dt d omega. That is what I have done is, that is induced this a omega and b omega over here and simplified it. It would give me this one, that is any function f x we could write as this in this form. So, let us see, we are going to use this Fourier integral in our solution. We have got the solution depending upon a parameter p as u x comma t comma p as a p cos p x plus b p sin p x into e to the power minus c square p square t. Now, let us define u x t as integral over this parameter p. So, we are taking this u x t as 0 to infinity u x comma t comma p dp. Now, if I write it out this one, what we are going to get it? We do get it at 0 to infinity a p cos p x plus b p sin p x, that is u x t comma p into e to the power minus c square p square t integrated with respect to p, that is d p. Now, the initial condition given is that u x at t is equal to 0, we are getting u x comma 0 as f x. So, first evaluate what will be u x comma 0, that is at t is equal to 0, I would get this term as 1. So, I would get a p cos p x plus b p sin p x d p is equal to f x, that is f x I should get I should get a p and b p in such a manner that I do get f x as this integral. So, using the just now we had done the formulas, we do know that is we could write a p as 1 upon pi integral minus infinity to plus infinity f v cos p v d v and b p as 1 upon pi minus infinity to plus infinity f v sin p v d v. Now, substitute this in our u x t, that is in its place of a p I write, if I substitute this in place of Bp, if I substitute this integral and then write this whole integral, what I would get in first, if I substitute over here, I would be getting is, after getting it, that is cos Pv and cos Px, sin Pv and sin Px, we could substitute it and we could write it as 0 to infinity minus infinity to plus infinity Fv cos Px minus Pv dv dp. So, what we would get ux comma t as this one. So, substitute Ap and Bp, this is what we are getting the solution of our heat equation or our initial value problem with Ap and Bp defined at this. So, now let us simplify this solution. I am writing it as substituting this Ap and Bp over here, I would get 1 upon pi integral, this 1 upon pi is constant, that I am taking out, integral 0 to infinity, Ap is the integral minus infinity to plus infinity Fv cos Pv and then cos Px dv dx. Similarly, the Bp we would be getting is Fv sin Pv and then sin Px and then e to the power minus c square p square t and this dp. So, again simplify as usual, that is we do write cos Px cos Pv plus sin Px sin Pv is nothing but cos Px minus Pv. So, we are getting is this integral as this function solution as ux comma t 1 upon pi 0 to infinity minus infinity to plus infinity Fv cos Px minus Pv into e to the power minus c square p square t dv, then integrated with respect to p, that is dp. Now, what this f is actually your initial condition. Let us simplify it little bit more. If I do allow that the change of order of integration is possible, that is the integral with respect to v and with respect to p, if I can interchange them and suppose that these integrals are existing, then this interchange is possible. So, let us say that these integrals are existing, so then this interchange is possible. I do get it first this integral minus infinity to plus infinity, since this integral is with respect to v and the second integral is with respect to p and f v is not containing any term of p, I am taking this out of this integral with respect to p. So, f v and then remaining functions with respect to p, that is integral 0 to infinity e to the power minus c square p square t cos Px minus Pv dp. Now, this inside integral, let us just try to find out this inner integral. Inner integral is 0 to infinity e to the power minus c square p square t cos p times x minus v dp. Now, what we are having is minus p square and then cos p, something like this one. So, we have to evaluate this integral. Let us come to the evaluation of this inner integral. If I see this cosine of theta, we do know that e to the power I theta I can write as cosine theta plus I sin theta, that Euler's formula we do know very well. So, cosine theta plus I sin theta, if I do take, there cosine theta is nothing but the real part of e to the power I theta. So, we do know from the complex integration that if I have to integrate a real part of any function, it is same as that integral of real part of the integral. So, we are getting it this function, if I do take, this function is actually the real part of this function. So, what the function we are having, e to the power minus c square p square t, we do know that e to the power I theta I can write as cosine theta plus I sin theta, that Euler's formula we do know very well. So, cosine theta plus I sin theta, if I do take, there cosine theta is nothing but the real part of e to the power I theta. So, we do know from the complex integration that if I have to integrate a real part of any function, it is same as that integral of real part of the integral. So, we are getting it this function, if I do take, this function is actually the real part of this function. So, what the function we are having, e to the power minus c square p square t cos p x minus p v, and the other function is e to the power minus c square p square t e to the power I p x minus v. its real part is this one, because e to the power I p x minus v we can write as cos p x minus v plus I sin p x minus v. So, using that one we do say is this is the real part. So, now let us evaluate this integral, complex integral, and then we will go for the real part of that integral, and that would be equal to this one. So, let us see this integral. For this integral we will simplify a little bit, because this integral is with respect to p and we are having c and t and x and v, so many things. So, let us assume a is equal to c square t. So, what I would get e to the power minus a p square, and then assume this x minus v as 2b. So, that I would get e to the power I 2b p. So, what we do get with this constants changing, now I am evaluating this integral 0 to infinity e to the power minus a p square e to the power I 2 b p d p with respect to p. So, take this exponent, all the exponent in one side, and then make it a whole square. So, what we are having is minus a p square plus 2 I b p. So, minus a I am taking out. So, p square, and it would be b upon a minus 2 I times b upon a p. So, what the term I do require, so this is what p square minus 2 I b upon a times p. So, what the function we do require, the term we require to make it the whole square would be square of I times b upon a. So, square of I b upon a, that I have added over here. So, that I have to subtract over here. From there, if I am subtracting, I have to get it out as plus sign. So, I do get a times I b upon a whole square. Now, simplify it. Since this term is e to the power a times I b upon a whole square, this is not containing any term of p, we can take it outside the integral sign. We do get it I square b square upon a square. So, a would be cancelling out, I square is minus 1. So, we do get e to the power minus b square upon a, and the term which is inside this integral, that is e to the power minus a p minus I b upon a whole square integrated with respect to p. Now, make the change of variable, take square root of a times p minus I b upon a as some other variable, say v. Now, because all the things we are using here, so I would not be making it v, I would again change it to the p. With that one, what we do get is that dp would be changed only to root a dp. So, what we do get it as actually this integral as e to the power minus b square upon a upon square root a, limit 0 to infinity, since this quantity inside this square one, that is with multiplied with square root a, we are making the change. So, if p is going to 0, the whole quantity will go to 0. If p is approaching to infinity, the whole quantity will approach to infinity. So, the limits would not change, and it is e to the power minus p square dp. Now, if you to remember, this is not a very nice function which we could say is we could integrate. This is not an elementary function which for which the integral is known to us. But if you do remember, when we are doing is this Fourier series and Fourier integrals, we had evaluated this integral once, and that integral was, which we had evaluated, that was minus infinity to plus infinity e to the power minus p square dp is equal to square root pi. We had evaluated there by changing it to the polar coordinates and making the multiplication of integrals as the multiple integral. So, if this function I do take e to the power minus p square, this function is even function with respect to p. That says is this integral minus infinity to plus infinity e to the power minus p square dp, I can write as 2 times integral 0 to infinity e to the power minus p square dp, and that is given as square root pi. So, I do get the integral 0 to infinity e to the power minus p square dp as square root pi by 2. Now, so this integral is square root pi by 2. Now, substitute this to this integral, what I would get it square root pi by 2, square root a is as such, and this e to the power minus b square upon a. This evaluation of this integral is square root pi by 2. Now, if I see this integral, this value, this is a real value, it is not having any complex term, it is real value. So, the real part of this integral is this one, which is would be same. So, what we have actually got? We have got that integral 0 to infinity e to the power minus c square p square t cos p x minus p v d p. This I have to substitute this the value of a and b whatever we had assumed over here. From there we do get square root pi by 2, a is c square t. So, square root a would be c times root t, e to the power minus b square upon a. B square means I would get x minus v whole square upon 4, a is c square t. So, I would be getting minus x minus v whole square upon 4 c square t. Now, this is what we have got, this inner integral. Now, substitute this inner integral in our solution. The solution was u x t as 1 upon pi integral minus infinity to plus infinity f v, then integral of 0 to infinity e to the power minus c square p square t cos p x minus p v d p, and whole thing is been integrated with respect to v. Now, this inner integral just now we had calculated. Now, let us substitute it. We get 1 upon 2 c square root pi t, because 1 upon pi is there and we have got square root pi upwards. So, the square root pi divided by pi would be 1 upon square root pi, that is what we are getting the constant, and since this is the constant. So, we can take it outside the integral sign. Then f v, and what is the, we have got e to the power minus x minus v whole square upon 4 c square t d v. This integral is with respect to v. Now, change the variable of integration. Now, rather than writing it with respect to v, let us use some new variable. The new variable, if you see, is we just want to simplify the term of this exponent. I am introducing new variable z as v minus x upon 2 c root t. So, you see is that is what is a here, either I write x minus v whole square or v minus x whole square, that does not matter. The thing which will matter is, since this integral is with respect to v, so this dz, when I would be writing, if I am writing it as v minus x, I would get the positively, that is it should be dv. dz is equal to dv upon 2 c square root t. So, if I change this variable of integration, as v is approaching to minus infinity, this z will also approach to minus infinity, because all others are constant. Similarly, as v is approaching to the plus infinity, z will also approach to plus infinity. So, what we would get, another formula 1 upon square root pi, because this 2 c root t, that will go with the dv, and I would get as dz. V I would get from here as 2 c root t z plus x. So, x plus 2 c z root t and e to the power minus z square dz. So, we have got the solution of our heat equation, or rather you could say we have got this as the heat flow in an infinite bar, as either by this formula, where 1 upon 2 c square root pi t integral minus infinity to plus infinity f v e to the power minus x minus v whole square upon 4 c square t d v, where your f is nothing but the function which is governing the initial temperature, or which is giving the initial temperature of the bar, or we may write in this another formulation, where we are writing it as 1 upon square root to root pi. So, you are finding it out that all these constants and all these terms have been simplified, the term only argument of f is been there, and that is also in the terms of x. So, we are getting is x plus 2 c z root t dz. So, this is what we are getting is the solution of our heat equation. Now, let us see is that is, if I do give any particular value, that is do an example, how do we do get the solution. So, let us do one example. Find the temperature in an infinite bar if the initial temperature is 100 degrees centigrade between minus 1 to plus 1 on the bar, that is on the bar we do have on the x side only the temperature is from minus 1 to plus 1, and C we are having is 1 centimeter per square per second. So, let us see what we have to solve this initial value problem. Del u over del t is equal to c square del 2 u over del x t, because it is infinite bar. So, my x has to be from minus infinity to plus infinity, t is positive. Initial condition we have been given that u x 0 is f x, which is actually a constant. Constant is been given as 100 degree centigrade, that is it is 100 in the range minus 1 to plus 1, and it is 0 elsewhere. If I just go ahead for solving this kind of equation, what we are being actually given, that if this is my infinite bar, what we are being given, that the initial condition is saying is that the temperature between this is 100 degree centigrade and all other points it is 0. So, this is my f x, this you see is this is my f x initially which is been given. Let us just move to the solution. So, I am not going to solve this equation again, just now we had solved it using the Fourier integral. We have got the solution as 1 upon 2 c square root pi into t minus infinity to plus infinity f e to the power minus x minus v whole square upon 4 c square t dv, that is the first formulation we are using. Now, here I will substitute the value of f is 1, f is 100 between minus 1 to plus 1 and 0 elsewhere. What we are assuming is all these integrals, that is whenever we do have a limit from minus infinity to plus infinity, the function is defined in a finite range, and other range if it is 0, even in the infinite range we take the integral to be 0. So, accordingly that we will substitute c is equal to 1, f v as 100 between minus 1 to plus 1 and 0 elsewhere. What we do get 100, that is a constant, I could take outside the integral sign. So, 2 times c is 1 square root pi t, and since it is 100 only in the range minus 1 to plus 1. So, the integral will reduce from minus 1 to plus 1 e to the power minus x minus v square upon 4 c square t dv. Let us try to solve this integral. We do know this integral, as I said, is not very nice function, elementary function. So, it cannot be evaluated as such. What we could do is we could find out the values of this integral which are being available in the tables. This is in engineering it is being called as error function, and those who are knowing little bit probability and distributions, they might be understanding that this is something is a density function of a normal distribution, and this we could say is that the probability under the normal probability curve, and there they can use these tables of those probability curves to find it out the solution, the values. Let us see is for different values of t, how does this look alike. If I change it to the that usual v minus x upon 4 c square t as z, we do get this in this one, and in the limit would be certainly changing it to this one. So, let us see. So, let us see is that how this function would look like for different values of t. When t is equal to 0, my function u x 0 is given this one. So, this is this one. When if we just put t is equal to 0 here, we will get actually this one. If I put t is equal to 1 by 8, you see this is the line which is this little bit pink color kind of line. This is coming as this curve is giving me the heat at t is equal to 1 by 8. As I move t to 1 by 2, this red color line, this is what we are getting is that heat equation, this solution u x t heat flow. If I take t is equal to 1, we are moving to this one, and if t is equal to 2, we are having this orange color of line. So, what we are having is that is as my t is increasing from 0 to this one, initially we had this square kind of this bar was having only the heat. Now, at t is equal to 1 by 8 time, the heat has been flowed, that is heat is now till here, and it is having this kind of function. When t is equal to 1 by t, the heat has been flowed till this point, and we had the flow of the heat in this, or this heat, the temperature is this one, and so on. So, the temperature is moving, that is with the time t, the whole bar is getting heated and the temperature is flowing, and in this manner we are going is that, and the heat is being equally being distributed. You could say that this is how we are getting it like. So, this is what is the flow of heat. Now, we had used in this one, because it was infinite var, we had used this Fourier integral. If you do remember in the Fourier transforms, the Fourier transform we have got using the Fourier integral. Will it not be nice if I do use Fourier integral in this solving this problem? Let us try to see can we use this Fourier transform, and we have actually done the not only the Fourier transform from the Fourier integral, we have got Fourier sine transform, Fourier cosine transform, and then the Fourier transform. So, all of them can be used over here. Now, let us see that is whether we can do those things or not. Before going to that, let us recall those things, so that we do remember that how do we can use it. So, Fourier cosine transform, if you remember, we had defined as that square root 2 upon pi 0 to infinity f x cos omega x dx, and its inverse Fourier cosine transform was f x square root 2 upon pi 0 to infinity f c hat omega cos omega x dx. We had used this two kind of notations, either this f c of f, that is the Fourier cosine transform of f, or we had used another term that f c hat omega, that is at omega we are getting it. Or Fourier sine transform, similarly we have defined as square root 2 upon pi integral 0 to infinity f x sin omega x dx. If you do remember, we have also used that is this constants may be differing, that is sometimes we are using the constants for transform as well as in the inverse transform, the equal constant, or sometimes in the transform we are not using any constant, and in the inverse transform we would be using 2 upon pi. So, here also inverse Fourier sine transform is square root 2 upon pi f s hat omega sin omega x dx, and the Fourier transform we were having as Fourier transform of f, we have defined integral minus infinity to plus infinity f x e to the power minus I omega x d omega, and the inverse Fourier transform as 1 upon 2 pi integral minus infinity to plus infinity f hat omega e to the power I omega x d omega. Here also the constant may differ, that is either we use in the inverse the constant 1 upon 2 pi and here no constant, or we use 1 upon square root 2 pi constant at both the sides. Now, you see in the Fourier transform we are having this integral from minus infinity to plus infinity, while as in the sine and cosine transform we are having this integrals from 0 to infinity, that what it says is my function f x is on the range 0 to infinity, that is x is on the 0 to infinity, and here x is on the minus infinity to plus infinity. Now, since we are using here our in heat equation the bar was infinite, that is from minus infinity to plus infinity. So, we would like to use this Fourier transform for having the solution. So, let us use this before using, let us use some properties as well, because without those properties we cannot use the Fourier transforms of derivatives, because we would be using them in the differential equation, that is we would be using it with respect to derivatives. So, this is one important properties which we have to recall. So, Fourier cosine transform of the first derivative is nothing but omega times Fourier sine transform of the f minus 2 upon pi f 0, and the Fourier sine transform of the derivative of f is minus omega times Fourier cosine transform of f. Fourier cosine transform of second derivative, if I just go ahead using it here again with this one, we do get the formula minus omega square Fourier cosine transform of x minus 2 upon pi f dash 0, and second derivatives Fourier sine transform as this one minus omega square, it should be Fourier sine transform of f x plus 2 omega upon pi f 0, and the Fourier transform of the derivative is I omega times Fourier transform of f, and second derivative we just get it minus omega square Fourier transform of f. One more important property was convolution, that is if I define convolution of two functions f and g as minus infinity to plus infinity f y g x minus y dy, then Fourier transform of the convolution is nothing but the multiplication of the Fourier transforms. So, let us use this Fourier transform in this equation. Now, assume this solution of this is actually u x t. Now, what we would be assuming is that is first we would be taking the Fourier transform of u with respect to x only. So, this is our initial value problem. Now, Fourier transform of if I take u as a function of x and the u as function of x and t, and we are taking the Fourier transform with respect to x variable, then if I take the Fourier transform on this whole one, this is u t, of course, it will involve x, its Fourier transform with respect to the variable x is c square Fourier transform of u x x. This is the derivative with respect to x. Since I am taking the Fourier transform with respect to x, so the derivative with respect to x, I can use the property of the derivative, which is nothing but minus omega square the Fourier transform of u, and c square is as such. Now, what is this f Fourier transform of u t? If I do allow the interchange of differentiation sign and integration sign, that is, let us write what would be Fourier transform of u t. This is nothing but by definition minus infinity to plus infinity u t e to the power minus I omega x d omega. U t is nothing but del u by del t. Now, if I say is that I can interchange the integration and differentiation sign, because this is function is involving only x, so there is no t term. So, I could treat it as the derivative of u into e to the power minus I omega x. I can write it as del by del t integral minus infinity to plus infinity u e to the power minus I omega x d omega. What it is? Nothing but this is the Fourier transform of u. So, we could write it as del upon del t of f of Fourier transform of u. What it says is I am getting Fourier transform of del u over del t as del by del t of Fourier transform of u. Now, if I write in this manner in this equation, if I do substitute, what I do get? I do get del by del t of Fourier transform of u is minus c square omega square Fourier transform of u. Now, I am taking this new function rather than as we used to have f x or something. Now, what we are having is this Fourier transform of u. This is a function of omega. So, this is a function of omega I am having. So, this is now my what my partial differential equation, if I do see, this has been changed to the ordinary differential equation, where I am having is it has to change with respect to t we are having, and this function is of omega and t. So, if I do solve it this differential equation with respect to t, this is the first order equation, we do know its solution would be now I am using another notation, that is for Fourier transform of u with respect to x at and t is as such, we are writing it u hat omega t is c omega e to the power minus c square omega square t. Now, why I have used this c omega? This would be actually a constant, since we are using the partial derivative with respect to t. So, this constant may depend upon the other variable, that is omega. Now, this constant c omega, that can be determined using my initial condition. Now, what is initial condition? If I take the Fourier transform of this initial condition also, because initial condition is also a function of x, then what I would get? U hat omega 0 is f hat x, that is the Fourier transform of u at omega 0 is same as Fourier transform of x. Now, substitute this one, what we do get that use this initial condition in the solution, what I would get? My solution would be Fourier transform of u with respect to x, that is u hat omega t is f hat omega e to the power minus c square omega square t. So, now to get u x t, what I have to do is I have to find out the inverse Fourier transform of this right hand side function. So, let us write it out, u x comma t as 1 upon 2 pi integral minus integral plus infinity f hat omega into e to the power minus minus c square omega square t inverse Fourier transform. So, I have to multiply it with e to the power I omega x, integrate it with respect to omega. So, now if I write what is f hat omega, if I use the definition, it is minus infinity to plus infinity f x e to the power minus omega x d omega, sorry dx, it should be dx. Now, because x is having both the places, the solution also I want to x. So, I will use here v, and then if I substitute this in this equation, what I do get u x t as 1 upon 2 pi integral minus infinity to plus infinity f v integral minus infinity to plus infinity e to the power I omega x minus omega v e to the power minus c square omega square t d omega d v. What I have done is substituted this one and then change the order of the integration. Now, why I have changed the order of integration? One is with respect to omega. So, this is with respect to omega and this is with respect to v. Again you see is that this is the similar form we have got when we are solving it using the Fourier integral. There we had solved this one. So, we are getting it the solution in the similar manner. What you see is that is here I do not have to go for that separation of variables, solving two differential equations and then making it the idea that is how to integrate or how to get the solution of the entire problem using the integration. What we have done is directly use the Fourier transform and we had come up with this solution. Now, you can simplify it again and you will get the same solution. From here, since we are getting it this e to the power I omega x and this f v and this e to the power c square omega square, if you see is what we could get one more idea, can't we use this convolution theorem? You see that is what we are saying. We are solving this problem, initial value problem, del u upon del t is equal to c square del 2 u upon del x 2, x is ranging on the whole real line, t is positive, initial condition u x comma 0 is f x. And when we use the Fourier transform, we got the solution as 1 upon 2 upon pi integral minus infinity to plus infinity f hat omega e to the power minus c square omega square t into e to the power I omega x d omega. What we are saying is this we are having Fourier transform of f and into another function e to the power minus c square omega square t. This is also a function of omega, function in omega, and multiplication of these two I want inverse Fourier transform of this. What it says is that if I treat this e to the power minus c square omega square t, if I say this is also a Fourier transform of some function g, that is what I am saying is let g hat omega, that is the Fourier transform of g x is e to the power minus c square omega square t. Then what we are getting, I am writing it is f hat omega into g hat omega and its inverse Fourier transform. What it says is, if I do have my convolution theorem says is f convolution g, the Fourier transform of f convolution g is f hat omega into g hat omega. So, what I would get f convolution g as inverse Fourier transform of f hat omega into g hat omega, and this is what we are getting is f hat omega into g hat omega. So, the solution should be the convolution of f and g. What is this g? That is we have to find it out. So, this is what I was explaining, that this says is u x t should be 1 upon 2 pi integral minus infinity to plus infinity f hat omega g hat omega e to the power I omega x, that is inverse Fourier transform of f hat omega into g hat omega. The solution has to be your convolution of f and g. The convolution of f and g, if you do remember, we have defined as minus infinity to plus infinity f p g x minus p d p. So, now the question comes is that is what is my g. Now, let us see this g. In the Fourier transform, we have done this as an example. There I have taken this example just because we would use it somewhere. You can just go ahead and find it out. It is we had find it out that Fourier transform of e to the power minus a x square, this is square root pi upon a e to the power minus omega square upon 4a for any a positive. Now, here what I am having is c square and t, t is positive, c square is already positive. So, this a positive is being satisfied. So, if I choose my a as 1 upon 4 c square t, I would get that g x would be 1 upon 2 c square root pi t e to the power minus x square upon 4 c square t x square. So, a is actually my 1 upon 4 c square t, that is what you are getting, and so here is square root pi upon a, that is again you would be getting it in the form of that one. So, we are getting this is my g x. Now, if I substitute this g x in my u x t, I would get u x t. So, this constant is with respect to t. So, this is complete constant. So, I could take it outside, integral minus infinity to plus infinity f p into e to the power minus x minus p square upon 4 c square t d p. Now, you see this is also the solution which we have got in the first problem. So, what we have seen is that is either I use this method of separation of variable, or I just come to this use the Fourier transform. In the Fourier transform also, rather than finding out inverse Fourier transform directly, if I do use this convolution result, my method becomes much cleaner, or you could say much nicer and elegant, and we get the solution. So, all these techniques, that is why this Fourier transform is called a technique. We are using these techniques, we are simplifying our problems. Now, in all these things we have taken this infinite bar. Now, if I do have to find out the heat flow in a semi finite bar, that is it is not minus infinity to plus infinity, but says from 0 to infinity. In that case my function would be defined from 0 to infinity, and in that case we can use Fourier sine or cosine transform. So, let us see is that is whether we can use it. So, first see is that is use of Fourier sine transform. So, now we are having our problem, the del u over del t is equal to c square del 2 u over del x 2, where x is from 0 to infinity and t is positive. So, again we are having semi finite bar with lateral insulation, and now we can introduce one boundary condition as well. So, with the initial condition u x at 0 is at t is equal to 0 is f x, and we can now impose one boundary condition that u 0 t is 0. Now, we have to solve this one. For this, now we are not going to use again this separation of variable method. Now, we will directly use the Fourier sine transform. So, what it says is I require the Fourier sine transform of del u by del t and del 2 u by del x 2. Again I will take the Fourier sine transform also with respect to x only, because what we are having is that is here initial condition is with respect to x, and with t we are getting is that is the boundary condition is 0. So, what we do get is f at 0 would be u 0 0, that is we would be getting it 0 itself. So, we just use the function the Fourier sine transform with respect to x. Again we use the Fourier transforms of the Fourier sine transform of the derivatives, that says is as we have done in the Fourier transform, this again we can write the Fourier transform of u t as del upon del t of Fourier sine transform of u, which is same as Fourier sine transform of u t. The sine transform we are taking with respect to x. This should be c square, it should be equal to c square times Fourier transform of u x x, that is according to this equation. And what will be the Fourier transform of second derivative with respect to the sine transform, that is minus c square omega square f s u, the Fourier sine transform of u, and then what we do have the constant, that is at f at 0. F at 0 from here, if I u at 0 0 we would get, because we want u 0 t, u 0 t is given as 0 initial boundary condition, that says is that constant which we would be getting here in the Fourier sine transform, that would give me 0. So, we would be reducing this one. So, now what again we have got the ordinary differential equation, that is this is now my function Fourier transform, Fourier sine transform of u with respect to x, and we are taking this equation derivative with respect to t only. So, we do get this ordinary first order differential equation, which is very easy, and we do know its solution is c omega e to the power minus c square omega square t, and the function what we would be getting is the Fourier sine transform of u at omega and t. Now, this c omega we can determine using my initial condition. What this initial condition gives me? It gives me, that is if I take the Fourier sine transform on both the sides, it gives me that Fourier sine transform of u omega 0 is Fourier sine transform of omega, for x it should be omega. So, if I just substitute it, what I do get, u omega at s omega t is f has set omega e to the power minus c square omega square t. So, we just find out u omega u x t as the inverse Fourier sine transform of this function. So, we can just use the inverse Fourier sine transform, using the inverse Fourier sine transform this one, and for f has omega this is what is Fourier sine transform for. So, for f s hat omega we do use this one, and for inverse Fourier transform we use this formula. What I do get is, so we do get u x t is equal to 2 upon pi integral 0 to infinity f p sin omega p e to the power minus c square omega square t sin omega x d p d omega. So, what we are getting is again if you do see is, that is because it is in the semi finite bar, you are getting the solution, nice neat solution in the terms of these functions. Now, we do know that we can simplify it, we do get it sin omega p here and sin omega x. So, we can write it as cosine of omega p minus omega x plus omega x minus cosine of omega p and omega x, like that we do get it. This would give me neat one, and then we can integrate it out. So, this is what we are using this Fourier sine transform, we can get the solution. So, today we had learned it that the heat equation, if I take the heat flow in infinite bar practically means very long wire or very long bar, that is all. We can solve it using, rather than using this separation of variable method, which was very lengthy one, and then we had used this Fourier integrals. We had also learned that is we can use the Fourier transforms, and in the Fourier transform if we do use this one more result, that is called the convolution result, we had find it out that the solution was coming out very nicely and neatly. Then if we are talking about semi finite bars, then we could use the Fourier sine transform, that is one method we had seen, or we could use, depending upon the other situations, what is the boundary conditions have been given or initial conditions have been given, we can use other transform. So, today we had learned the heat equation using the Fourier transforms and Fourier sine transforms. Thank you.